Hey guys, welcome to the Curiosity channel. I love to draw, especially with crayons. I'm not very good at it, but that doesn't matter. It's the fun of doing it that's important. But it's really hard to draw something if you don't know what it looks like. For example, what does an atom look like? While mankind has known about the existence of atoms for over 2 centuries, very few of us have a very concrete idea in our minds of what an atom actually looks like. Those of us who do are probably picturing something along the lines of a globule of spheres in the center here, with more spheres whizzing around it in circles. But that's not exactly accurate. You see, that's the Bohr model of the atom, which is what you'll commonly see in pop culture and chemistry textbooks. But let's go a step further. Before we dive into a full explanation of this most recent model, we're going to have to go into a little bit of history. This takes us, of course, back to the Grecian philosophers. The first recorded hypothesis of an atom, or any elemental particle, is by the Grecian philosopher Democritus. Completing most of his work in the 5th century BC, Democritus proposed that the world was composed primarily of two different substances: empty space, which he called the void, and matter, which he supposed was composed of infinitesimally small particles. These particles, Democritus claimed, were both homogeneous and indivisible, the same substance throughout, and uncuttable. Hence his name for them, the Greek word for uncuttable, atomon. Democritus suggested that the qualities of these atoms would make up the properties of the objects they composed. Water atoms, for instance, would be round and smooth, thus creating the experience of water we know today, whereas iron atoms would be rough and jagged and catch onto each other, creating the rigid substance we know as iron. Aside from these differing shapes, however, Democritus would have said that all of these atoms were of the same size and mass. Now, from a modern perspective, we can look back and see a lot of things Democritus had right. It looks very similar to our modern atomic theory. However, scientific experimentation at the time gave little support for this atomic theory, and Aristotle's claim that matter was continuous, could keep being undivided into eternity, reigned as scientific law. In 1803, meteorologist and chemist John Dalton made a significant leap forward. While studying elemental gases, he learned that each of these gases had a unique mass on a particulate level. From this discovery, Dalton was able to pioneer the first scientific theory of the atom, proposing that every element was made up out of unique, smaller particles that composed it. Now, there were a few problems with Dalton's theory of the atom, but the important thing is that this was the first time that there was any scientific and testable theory of the atom proposed to the scientific community. The next major model of the atom was introduced in 1904 by British physicist Jonah Jameson Thomson. Thomson developed his own theory of the atom while experimenting with cathode rays. Conventional theory at the time assumed that cathode rays were some sort of ethereal energy. While testing this theory, Dalton discovered that cathode rays were instead a result of ionizing an elemental gas. Some positively charged portion of this gas would remain behind, while a negatively charged portion of that gas would shoot out in the form of a ray. This was staggering from Dalton's model of the indivisible atom, because it revealed that this atom was actually comprised of two separate elements of differing charges. Thomson's research also revealed that these negatively charged particles, which he called corpuscles, were dramatically less massive than the remainder of the atom from which they were separated. In light of this evidence, Thomson created a new theory of the atom, in which there was some positively charged mass with negatively charged sprinkles all throughout. Physicists later came to call this model affectionately the plum pudding model. In 1911, New Zealand-born physicist Ernest Rutherford challenged this model of the atom with the results of the data he gathered while shooting positively charged radioactive particles at a sheet of gold foil. This is science, guys. Rutherford was shooting these alpha particles at a sheet of gold foil, and just as predicted by Thomson's plum pudding model, some of the particles just bounced straight back at the emitter, but some of them continued straight on through, deflected or some of them even unaffected by the gold foil. From this, Rutherford was able to determine that atoms are comprised of a positively charged center and negatively charged particles surrounding that, and in between was, stunningly, empty space. Rutherford's model was the first of the so-called planetary models. There was only one issue with this model, however. While it did explain a lot of experimental data that they'd collected so far and predict a couple new findings, it didn't make any sense. You see, it was unstable. All of those negatively charged particles should be careening towards the center, collapsing under its own weight. Right on the tail of this discovery, Danish physicist Niels Bohr took the model a step further by applying the new ideas of quantum mechanics. He recognized Rutherford's improvements in this area, but he also recognized its faulty reliance on classical mechanics, an approach to physics that was quickly becoming outdated. In 1913, Bohr released an updated model of the atom. Applying Max Planck's research into quantization of energy to the concept of negatively charged particles circling a positively charged nucleus, Bohr suggested that each electron could occupy an orbit of a specific size and speed, each associated with a specific amount of energy. This new model explained the recent evidence discovered by Thomson's experimentation, but it also resolved the issue with the instability of Thomson's older model. However, in 1927, Erwin Schrödinger, yes, the one with the cat, created a new model. Fully applying the ideas of quantum mechanics and mathematics, Schrödinger developed an equation. Revolutionizing modern physics, Schrödinger's equation is equivalent to Newton's laws of motion when it comes to quantum mechanics. Among the more esoteric applications of Schrödinger's equation, implying quantum tunneling and even that matter itself may just be a different form of energy, we find our model of the atom. According to Schrödinger's model, the nucleus of the atom sits in the center, comprised of both positively and neutrally charged particles. And around that, we find not electrons moving in an orbit, but a cloud of possible locations for that electron. You see, the Heisenberg uncertainty principle states that we can only know either the velocity, speed and direction of motion, or the location of a specific subatomic particle. We can't know both. And since we know the angular momentum of each of these electrons, we cannot know where they are at any given time. So in our new model of the atom, we have our nucleus in the center, and around it are simply clouds of possible positions of electrons, which we still call orbitals for convenience's sake. This model of the atom, derived from Schrödinger's equation, gives us our most up-to-date, most accurate model of the atom, fully accounting for quantum mechanics. Schrödinger's model has accurately predicted new experimental evidence for nearly a century, and is still the clearest picture we have of what things look like on an atomic level. As of 2019, Schrödinger's model has yet to be surpassed by any newer scientific theories. But maybe that'll be you. For now, get out there, think small, and stay curious, my friends. Hey guys, hope you enjoyed this video. If you did, go ahead and hit the like button down below. Let me know I'm doing something right. If you had any questions I didn't answer in this video, or any questions you'd like to see answered in a later video, go ahead and drop them in the comments section down below. If you'd like to keep up with the latest from the Curiosity channel, go ahead and hit the subscribe button, ring the bell. That'll keep you notified every time there's an update. Thanks again, and I'll see you next time.